we're going to talk about appearance next. So when we talk about appearance, or we describe appearance, the light which illuminates an object will be altered by its interaction with the material of that object in many ways and in many directions. The resulting light distribution is what gives us the visual impression, or the appearance, which we perceive for the object. So the appearance is more than just the color of the object. It's really the whole package on how that object affects light that falls on it. Although the appearance of different materials is the result of complex factors, the problem can be simplified by separating out two main types of appearance. The color, which is caused by the colorants, the dyes and pigments that are put into the material. The geometric characteristics of the light, the gloss, shape, and texture of the material. What is the surface like on the particular part we're looking at? So we can do this by separating out the energy re-emitted by the material into the diffuse reflectance, or the color, and the specular energy, the specular reflectance, the mirror-like reflectance off of the surface, or sometimes we call that the gloss. And there are instruments that are out there that are called gloss meters, where you can get an actual number on the gloss. But by separating out two types of energy, it's possible to identify each of the components and then select the most suitable instrument and geometry to measure and analyze color. So depending on what we're after, one of those geometries would be better than the other one. So we'll look at what those are. Definitions here. Specular means mirror-like reflectance, not affected by the sample itself. Spectral has to do with the different colors of light that fall on the object. And diffuse means the scattering of light from beneath the surface. So the light actually penetrates the surface, interacts with the pigment particles, and then is reflected out, and then we see that as the color of an opaque object. Two different sources of what we see. Specular reflectance does not produce the color. Diffuse reflectance produces the color. So our body color, the light interacting with the colorants in the material, and how the light reflects off the surface, we talk of in terms of gloss and texture, luster, lightness, and we'll see how the gloss or the texture of the material can affect the lightness of that material. So the color is caused by the selective absorption of some of the wavelengths of light and reflectance of others, so we can perceive that particular color. The energy is re-emitted as characteristic of that material, its color, and its composition. And then on the other hand, specular reflectance gives us the impression of that object as either being a shiny object, a satin finish, a matte finish. You know, when you go to the paint store, you can buy paint, either glossy paint or a satin finish, which is duller, or flat, which is the dullest of all. Metals can be identified by larger specular energy than other products, and smooth surfaces generally appear to be more glossy than rough surfaces. So think of a shiny piece of metal like the side of your car. It has a lot of gloss to it. A lot of specular reflectance comes off of that surface. So the specific definition of gloss, nice wordy scientific kind of definition, is angular selectivity of reflectance involving surface-related light responsible for the degree to which reflected images can be superimposed on a surface. So if you can see an image on the surface of an object, that's a glossy surface. It's a shiny surface. A hazy surface is one, if you look at the image, it's not quite as sharp. It's not quite as, it's wavy. It doesn't look as good when you see a reflective image. That's what haze is. It's not as sharp of an image. Specular reflectance looks like this. The light hits the object, bounces off in a very specific angle, especially if it's a real shiny object. Another picture of what that looks like of a smooth surface. The light comes in, bounces off in a very specific angle. If it's a rough surface, the light comes in, but now when it hits the surface, it's reflected different directions on different angles. It doesn't all go in the same angle. And then we can have diffuse and specular reflectance due to scattering from beneath. So we get both types. So any kind of objects really has both type of reflectance, specular reflectance and diffuse reflectance. So all these occur through either absorption or transmission of light, the majority of the objects. So what we can be present are both of those, like I mentioned, either in transmission or in reflectance. And it can all happen at the same time, especially if it's a translucent material. So we can measure this. The graphs that we get show how much light energy is reflected off of the surface wavelength by wavelength, or our object curve. So the spectral reflectance graphs are produced, and thus any numbers that are calculated from them will be different depending on the type of instrument and the geometry used to measure that sample. The idea is if you have a 045 instrument, it'll measure like we were just looking at that panel. It will not collect the specular reflectance that comes from the shiny surface if you're not looking at it at that angle. So it'll show a darker number for the shiny surface than the matte finish surface. Lower number for the shiny surface than the matte finish. The matte finish would be higher because there's more light coming off of it. The idea of the sphere is it doesn't matter what the surface looks like. It collects all the light in every direction. So you would get the same number for both. That's the theory anyway. It's not exactly that, but if we have a panel, and this shows, the slide shows numbers that are produced from the same glossy sample, you notice that they are different depending on which geometry that's used. So what these numbers represent is the lightness. We talked about hue, lightness, and chroma. Lightness values is L, chroma values are C, and hue is the H there, and then the last number here, delta E, is the total difference. So we're using the spherical instruments, the D/8:I is the spherical instrument, with the spectral component included. Okay, and then we measure it on a 045, we see that the numbers, and really where the numbers are the biggest difference, is in the lightness. The 045 is lower, so that's much darker, like we talked about. The spectral component excluded, which tries to mimic what the 045 instrument does, is higher than the 045, but it's lower than the spectral component included. So it's kind of in between there. That shows that there's differences, and those numbers for the same basic amount of pigment are pretty big for the differences. A difference of 8.3 is really quite a bit of difference. Even 4.7 is different. If you're doing a color match, you would never say that those numbers match. We look at this. The 045 instruments generally observe the object in conditions similar to the natural observations by our eyes. The instrument analyzes only color of the object, excludes the gloss. The sphere-type instruments illuminate the sample in a diffuse manner and then observe it at 8 degrees from the perpendicular. That sphere is painted white and collects all the light. So it collects all of the specular reflectance and all of the diffuse light. And since the specular energy is included in the measurement, the resulting graph and numbers are included in the color due to the material as well as the gloss of the object. So you would get a curve that is higher for the integrating sphere, higher up on the scale, than you would for the 045 because it's collecting more light. Talks about how there's a port there where we can exclude some of that specular energy, but it doesn't exclude all of that specular energy. This is kind of a picture of how the light is reflected off of different surfaces. If it's a very highly glossed sample on the right here, almost all of the specular reflection goes in that angle, a little bit off, but most of it goes that way. If it's a matte finish, it's pretty much uniformly spread in all directions. In a semi-gloss, most of it goes that way, but there's some that goes another way. So there's a kind of a continuum from very shiny to very matte finish. And the opening is relatively small in our integrating sphere. So it doesn't get all of that reflected light from the specular reflectance, so that's why the numbers don't affect it exactly. So because more of the specular reflection makes it to our eyes when we are looking at a matte finish, unless we are looking at the maximum specular reflectance angle, it appears to be lighter than a shiny sample. And then there's a picture in your book that pretty much looks like this panel I showed you, and I don't know how good it shows there. The idea is that the glossy surface should look darker than the matte finish. And in your book, it probably looks a little better than on that screen. But it also worked with this panel. It's really the same thing. If somebody asks you, say on a test, if you have a panel that has a matte finish on it and a glossy finish on it, and you looked at them, which one of those surfaces would look lighter? Now, hopefully, after all this, who thinks the matte finish is light? You got to raise your hand once. Matte finish lighter. Shiny surface lighter. The shiny surface is darker, so the matte finish is lighter because the matte finish reflects the specular reflectance, but the shiny surface, glossy surface, doesn't. So the next slide shows some applications for the two types of geometries and where you might use one versus the other. So first, surface reflection is how much gloss is present. So if we look at this table here, what we have are what the sample characteristics are in the first column, what we're after, what are we measuring, why are we doing the measurement, then our spherical instrument and our 0.45 degree instrument, whether they fit that condition. So if we have opaque samples having the same first surface effects and we're measuring color difference only, doesn't matter. We can use either one of those. If we have samples with first surface and color difference, and we want to measure the visual, how it looks visually, what that difference is, the 0.45 instrument is preferred over the spherical one. If samples with the first surface and color differences, and we want to measure color difference only, if we're doing a color match, for instance, and our sample that we're making has a different texture, say, than maybe our standard has, so we want to know what the color is, we would rather use a spherical instrument versus a 0.45. If the samples are transparent or translucent, we need to measure transmittance. We have to use the sphere because the 0.45 instrument can't measure in transmittance. And if we're doing color matching applications, if we're matching samples with varying first surface effect, varying amounts of gloss, surface differences, we would use the spherical instrument, not the 0.45 because it's affected by the gloss. In color matching application, where matching samples with the same texture to them, doesn't really matter which one. And the last one there is a different kind of problem where we measure metallic or special effect pigments. There's actually a special kind of instrument that's used. It's called a goniospectrophotometer that measures the light in a whole bunch of different angles. Our spherical spectrophotometer probably cost, I don't know, $15,000. A goniospectrophotometer would cost $100,000. I know Schulman over at Sharon Center has one of those. They're doing a lot of work with. There's a French company that makes them that we have actually one of their programs here, and we're trying to weasel one of those spectrophotometers out of them. But so far we haven't had any luck. Somehow they don't want to give us a $100,000 piece of equipment.